friends, my viewers at home. We are here again for another episode in chemistry, and today we're going to be taking on a very interesting aspect of chemistry, which talks about what you can see right on the board, the screening effect, which we also call the shielding effect, to shield. Exactly. Now, please, if you have not subscribed to my YouTube channel, please do so. We want your comment, we want your subscription, your likes, and all of them, and also share to your friends. Now, we enter this topic briefly to talk about what we call the screening effect and the shading effect. And in this aspect of this topic, we are going to be performing some little calculations that will help you more. And it will, like, this topic is ascribed to what we call, like, it's connected to the periodic table, which sooner or later in our YouTube channel I'm going to be posting those topics in a simplified format. Now, what is shading effect or screening effect? It is a phenomenon whereby the nucleus reduces its force of attraction on the valence electron. Due to the presence of the electron found in the inner shell. Now, your major concern here is talking about what? The nucleus and what? The nucleus, the valence electron, and the inner electron. They are what formulate what we call the screening effect. Now, what is a valence electron? The valence electron is the total number of electrons found in the outermost shell of an atom or orbit of an atom. Now, it's also interesting to also know that the ability of the nucleus to be reduced in its attraction to this valence electron, or because of this inner electron, is what we call what now the shielding effect. If not, there will be an attraction, being that the nucleus is positively charged. Exactly. Now, it's also interesting to know that if this is the way an atom is being represented, now this is the nucleus, which is positively charged. We have three shells here: shell 1, shell 2, shell 3, or orbit 1, orbit 2, orbit 3. Orbit 1 and 2 contain 2 and 8 electrons respectively, while orbit 3 or shell 3 has a total number of 1 electron, and it is that outer electron here that makes up the what now? The valence electron. Is that clear? Now, it's also interesting to know that as the number of shells is increasing, what happens? The screening effect or the shielding effect is what is increased. And if it is increased, there is a decrease in what now? In ionization what? Potentials. Is that clear? Now, what happened? Now, take note that screening effect increases due to the increase in the number of shells, which I've said just now. And I've also said that there is an increase in screening effect down the group. Why? Because of the addition of new shell as the what now? As the atomic number is being increased. And we said that there's a decrease of the screening effect across the period. Is that clear? Now, we also said that it also involves what now? That it also involves the shielding of what? The outer electron. The shielding of outer electron by what now? By inner what? Electron. And it also prevents outer electrons from what we call the effective nuclear charge, which you will soon see. And from there, we perform a little calculations in them. Now, a quick recap. We talked about the screening effect, and we gave it a definition that the screening effect talks about the reduction in the force of attraction of the nucleus on the valence electron due to the presence of electrons in the inner shell. Now, it is this inner shell you are seeing, which is the 2 and 8 electron. They are what forms the core electrons or the non-bonding electrons, as you will see in our next clip. All right. Now we move ahead closely to a very good aspect again, talking about the effective nuclear charge. The effective nuclear charge. Now, effective nuclear charge can be represented with the symbol ZeF, which is this effective nuclear charge. Now, it is the net positive charge that is experienced by an electron or by an electron in a multi-electron atom, or you can say that it is the net charge that is fed by an electron when it is in an atom. Is that clear? Now, the formula for it is effective nuclear charge is equal to the number of protons, which is Z, minus the number of core electrons, core, C-O-R-E, core electrons. Now, you can see here, I said Z is the number of protons in the nucleus, while X is the number of electrons between the nucleus and the electron in question. Now, we said that this X you are seeing here can also mean the number of non-valence electron, the number of non-bonding electron, or the number of electron that is not involved in bonding. So you see the names that they call it. Now, we are going to be solving some questions here, because this aspect of chemistry has posed a great problem to many students around the world. So I'll be taking my time to explain them. So you just relax and get the trick in it. Very simple. It is very, very simple. Now, the question says here, consider neon atom, sodium ion, fluoride ion. And the question now says, calculate the effective nuclear charge of each of these species you are saying here. Now we'll start with the first one, which is neon. Remember that neon has the atomic number of 10. Is that clear? Now, and from the formula, which is ZeFF is equal to Z minus what? X. Z here, which is the number of protons, is 10. While to get for X, which is the number of core electron or the non-bonding electron, we first of all write the what now? The electronic configuration for it, which is 1s2, 2s2, and 2p6. Now, from this neon atom now, the number of valence electron here, is 8, which is group 0, group 8. While the number of core electron or non-bonding electron here is 2. So from here I can say ZeFF is equal to what now? 10 minus 2 is equal to what? Plus what? 8. That is it. Alright. Next one on our list is sodium ion. Now, listen. For sodium ion, having atomic number of 11, follow. Now, the formula, which is ZeFF, is equal to Z minus X. Z here, which is the atomic number, is 11. Now, to be able to get for X, again too, you write the electronic configuration for sodium ion. Remember that sodium ion will lose one electron. So now we have what we call 1s2, 2s2, 2p what? 6. Having the configuration state of what? Of neon. So the valence electron here is what? 8. But the core electron here is what? Now is 2. So here is 2. So here become ZeFF is equal to 11 minus 2, which is what? Plus what now? 9. Is that clear now? Now the rule will change when I'm not talking about for that of what now? Sodium atom. Sodium atom have atomic number of 11. You are aware. Now, if I'm to make use of the ZeFF, excuse me, So here becomes Z minus X. Now you are aware Z here is 11, but the number of core electron here, we have to write what the configuration for sodium ion or for sodium atom, which is 1s2, 2s2, 2p6, 3s1. Now please take note. The valence electron here, the valence electron for sodium atom is 1. Is 1. No longer like the other one before, because sodium belongs to group 1. And if I have to make use of the normal share method, which is 281, you find out that the valence electron of sodium is 1. So the number of core electron, which also say non-valence, non-bonding electron, is 2 plus 2 plus, which is what, 10. So that becomes 10. So ZEFF is equal to 11 minus 10 equal to what? Plus 1. You see how easy they are. Now we're going to be talking much further. Alright. The next one now is fluoride ion. Simple. So what do we do? ZEFF is equal to Z minus X. Same thing. Z here is 9. The number of core electron, non-bonding electron, write the configuration state, which is 1s2, 2s2, 2p6. Remember that because fluoride ion, no matter they gain, and if they gain, they become what? Negatively charged. That's why you see that fluoride ion here is 1s2, 2s2, 2p6, having the configuration state of neon. And neon valence electron is what? 8. 2 plus 6, because these two have the same energy level. So it is 2 plus 6, which is what? 8. So the core electron here is what now? Is 2. So that ZEFF is equal to 9 minus 2 equal to plus what? 7. Now the next special we're going to be working on now is bromide ion. Now for bromide ion, you are aware that Z here has atomic number of 35. Now then, to get the number of core electron, what do? We first of all write the what now? Electronic configuration of what now? The bromide ion. Bromide ion, meaning it's going to gain 1. So we have to write for 36 electrons now. So we will now say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now we are going to rearrange this configuration to obey the what now? The Abel's rule, which states that electrons first of all that electrons we move into lower energy levels before moving to what now? Higher energy levels, so we can get our answer accurately. So I can now rewrite it to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. So from here now, we now understand that this state here now is now being a state of what now? Of an inert gas, whereby these two are the valence electron, while the other electrons here are the core electron. So when you count it, 10 plus 6 plus 2 plus 6 plus 2 plus 2, we have a total number of 28 what? Core electron. Thereby, the effective nuclear charge is now equal to what now? It is now equal to 35 minus 28 is equal to what now? Plus what now? 7. That's the final answer to what you are seeing here. Now, this is your own work to do. Calculate the effective nuclear charge of the following, which is molybdenum 3 ion, tungsten 3 ion, potassium ion, and calcium what? Atom. So when you do it, you can drop your answers on the comment section. God bless you. Thanks for your time. Bazooka loves you. God bless.